My dear students, I hope this finds you well. My name is Musyoka David, and I would like to take you through the chapter of radioactivity. Radioactivity, from 4 chapter, physics. Today is the day 29th, 6th, 2020. Our objectives will be, we are going to define radioactivity plus other terms like we are going to define atomic number, because we are going to define mass number, isotopes, etc. Of course, after that we are going to describe briefly the structure of an atom, and this will lead us to the cause or the origin of radioactive decay. Then finally we are going to describe briefly the 3 types of radiations produced during the process of radioactivity. Now, as far as the introduction is concerned, the introduction of, if you have a uranium compound, uranium is one of the radioactive materials or radioactive compounds, and then you have an opaque object, and then you have a photographic plate. Of course, the photographic plate will act as the screen. The photographic plate is the opaque object, which is usually metallic. This one is metallic. And then you have the uranium compound. Of course, this experiment was first undertaken by Henry Becquerel, a French scientist. He realized that an image of this object is going to be formed on the screen, and this of course shows that uranium produced radiations. If you have uranium compound, you have an opaque metallic object, and then you have a screen, then you have such a setup. An opaque an image is going to be formed on the screen, and this one will show clearly that uranium produced radiations. So this phenomenon was discovered by Henry Becquerel, but the other scientists who equally did their fair share of work in this field, and this phenomenon is what we call radioactivity. It's going to be our chapter for today. We start with the structure of an atom now. The structure of an atom. Structure of an atom. An atom. Structure of an atom. An atom is made up of 3 types of particles. Of course, we have, we have protons. This one is a recap of Form 1 work physics. We have neutrons, and we have electrons. You remember we said that protons are positively charged, electrons are negatively charged, but this one carry no charge. This one carry no charge. So basically the structure of an atom is like this. You have this is the structure of an atom. This is what we call the nucleus of an atom. This is what we call the nucleus of an atom. And actually in the nucleus of an atom, that is where the protons and the neutrons are concentrated. So the nucleus of an atom is positively charged because of the protons in it. Remember, the neutrons carry no charge. And then the electrons revolve around the nucleus in an orbit. The electrons revolve around the nucleus in an orbit. So the electrons are usually held by the force of the nucleus. The force of the nucleus that keeps them and their orbit. So basically this is the structure of an atom. The electrons revolve around the nucleus in what we call energy shares. And then we are going to define some terms. We define the first term that we are going to define is going to be the atomic number, which we denote by letter Z, and It's actually the number of protons in the nucleus of an atom. The number of protons in the nucleus of an atom. Nucleus of an atom. It is the number of protons in the nucleus of an atom. So you can actually define it also as the number of electrons, because you know that the number of protons and number of electrons in an atom is neutral. So an atomic number is the number of protons in the nucleus of an atom. We define another term which is mass number. Mass number, we denote it by letter A. This is actually the total number of protons and neutrons in the nucleus of an atom. In the nucleus of an atom, the total number or the sum of protons and neutrons, the sum of protons and neutrons in the nucleus of an atom. Then we are going to denote N. We are going to take N to denote the number of neutrons in the nucleus of an atom or in an atom. So basically we are going to have an equation. We will have an equation that mass number will be equal to the number of protons, which is Z, plus the number of neutrons, which is N, because mass number is the sum of protons and neutrons. So we are going to have A is equal to Z plus N. So actually given the mass number and the atomic number, you can get the number of neutrons. Given this one, you can get this one. So for example, we are going now to be representing an atom, like an atom of hydrogen. We are going to represent it. We shall have a 1 as the mass number and a 1 as the atomic number. If you have another atom X, in general now, in a general case, we have the mass number is A and the atomic number is Z. If I move on to helium, you know helium, the mass number is 4, the atomic number is 2. And then finally I can demonstrate using neon. Neon, the mass number is 20, the atomic number is 10. So that is basically how we represent an atom. We define another term which is isotope. We define an isotope or isotopes in the plural. An isotope, these are atoms with same atomic number but different mass numbers. Atoms with the same atomic number. They have same atomic number, same Z, but they have different mass numbers. That is different mass number. That is different A. So isotopes are atoms with the same atomic number but different mass numbers. For example, an example of an isotope is carbon. Because for carbon we have carbon 12, which is normally written as 12, Ca6, and then we have carbon 14, which is written as 14 carbon. So these are isotopes. They have the same atomic number but different mass number. So that is what we call an isotope. A good example of an isotope. Then we move on to another subtopic, basically which we have as nuclear stability. For a nuclide to be stable now, or for an atom to be stable, or for a compound to be stable in a nutshell, the number of protons in it must be equal to the number of neutrons. For a nuclide, for example, a nuclide of uranium that we saw in the beginning in our introduction, uranium. For a nuclide of uranium to be stable, the number of protons in it must equal the number of neutrons in it. But you realize that as the atom becomes heavier, this ratio may not be obeyed. This ratio may not be 1:1. There is a deviation from this ratio. There is a deviation from this ratio. And once the ratio is not obeyed, then that nuclide becomes unstable. And if it is unstable, then you know it is most likely to disintegrate. It is most likely to undergo radioactive decay, or to undergo what we call radioactivity, in order to achieve stability. For instance, if the ratio is 2:1, this one is not stable. It will strive to achieve, and in the process of disintegrating, in the process of decay, it will produce radiations. 3 types of radiations will be produced. We are going to come to that as we move on. So basically, if I draw a graph like that one, that graph is, here I have the number of neutrons, and here on this x-axis I have the number of protons. For a nuclide which is stable, it will lie along that line. This is normally, you know, the line y is equal to x. It will lie along that line. If it lies along this line, then the number of neutrons in it is equal to the number of protons in it, and the ratio will be 1:1. But those nuclides that lie here, they have more protons than neutrons, and so they are unstable. They will disintegrate to achieve stability. Those that lie here above the stability line, these ones have more neutrons than protons, and so they will disintegrate to achieve stability. So that is basically the origin of this radioactivity. If the ratio is not 1:1, then we have disintegration in order to achieve stability. So in our next small subtopic now, we are going to move on to what we call now we can now define the term radioactivity. We can now comfortably now define the term radioactivity. So we define radioactivity as the spontaneous disintegration, of an unstable nuclide to form a stable one, with emission of radiations. It is a spontaneous. It is not actually a very conducive process. It is a very rough process. That is why we use the word spontaneous disintegration or spontaneous decay of an unstable. It must be unstable nuclide to form a stable one. And in the process, we are going to have emission of radiations. These keywords must feature in your definition. Or alternatively, you can define radioactivity as the disintegration of unstable nucleus with emission of radiations in order to attain stability. So you must have disintegration of unstable in your definition. And then we must see the result of that spontaneous activity. We must have radiations being produced to achieve stability. Then now in our final segment, we are going to come to what we call types of radiations emitted. Types of radiations emitted during this radioactive decay. We have different types of radiations that are emitted. The very first one that we are going to briefly discuss is the alpha particles. The alpha particle. This will be written as alpha particle. It is basically an alpha particle is basically an helium nucleus. Basically an helium or a helium nucleus is a helium nucleus. It is usually written this way. This is how we write helium nucleus. This is what we call an alpha particle, and it is positively charged. It is positively charged. And then this one, it is less deflected. We are going to see the deflection. It is less deflected by electric and magnetic fields compared to the other one that we are going to say. There is another one that it is less deflected. We are going to come to that into details. Those are just fine, smaller details. So then we have the other type of radiation that is emitted. We have the other type of radiation that is emitted. We have the beta particle. Number 2, the beta particle, which is abbreviated beta. This is actually not B. It is a beta particle. It is a Greek letter in the Greek alphabet. Is a beta particle. A beta particle, it is simply an electron. Remember we said that an alpha particle is a helium nucleus. A beta particle is simply an electron, and it is abbreviated like this. -1 subscript here. So you can see basically it is negative. This one is positive, and it is negatively charged. It is negatively charged. Then finally, the type of radiation emitted during radioactive decay is a gamma radiation. Gamma is a very dangerous one. It is simply enormous amount of heat energy. High amount of heat energy. High amount of heat energy. It is high amount of heat energy which is produced. So basically now, if a radiation, if a nuclide is not stable, if a nuclide is not stable, it undergoes radioactive decay. And we have seen this also, that unstableness. It undergoes radioactive decay, and in the process of undergoing radioactive decay, it produces these 3 types of radiations: an alpha particle, a beta particle, or a gamma radiation. So a gamma radiation is simply high amount of energy. And then finally now, alpha decay. What happens during alpha decay? Alpha decay. If a nuclide X, this is alpha decay. Alpha decay. If a nuclide decays by release of an alpha particle, its mass number, decreases by 4, and its atomic number decreases by 2. Its mass number decreases by 4, and its atomic number decreases by 2. For instance, if you have X, the mass number is A, the atomic number is Z, and then it indicates emitting an alpha particle. An alpha particle is written this way. is how we write an alpha particle. If it decays by that, then it will form another stable nuclide. Now, why? It will form another stable nuclide. Why? And the atomic number of this one will be A minus 4, and this mass number will be A minus 4, and atomic number will be Z minus 2. Notice clearly that when you add Z minus 2 plus 2, you get Z. When you add A minus 4 plus 4, you get A. So this is the balanced equation. So when a nuclide X decays by releasing an alpha particle, it forms another stable nuclide Y. So in the process of decay, its mass number will decrease by 4, you see, and the atomic number will decrease by 2. This is what we call the parent nuclide. This one. This is mzazi, the parent nuclide. And this one is what we call now the daughter. And then this one is the alpha particle, this one. So if a nuclide decays by release of an alpha particle, the mass number decreases by 4 and the atomic number decreases by 2. And it is shown by this. Then now, let's see the other type. And before we give the other type, we can give an example. For instance, now you could have uranium, which is 238 mass number, and the atomic number is 92. If it decays, releasing an alpha particle, that is an alpha particle, then the mass number decreases by 4 and get 234. And then the atomic number decreases by 2, you get 90. And this one is thorium. Now thorium is stable. This uranium is unstable. Now thorium is stable, uranium is unstable. So this is the equation. Let's now move on to beta decay. Beta decay. We are through with alpha decay. Now we go to beta decay. If a nuclide X decays by release of a beta particle, it forms another stable nuclide Y plus the beta particle. The beta particle is written as what? We said a beta particle is an electron, like that. This is A, mass number, atomic number Z. The mass number remains the same, but the atomic number increases by 1. Notice that Z plus 1 minus 1 becomes Z. A plus A should be equal to A plus 0. So this should balance. This plus this should be equal to this. This plus this should be equal to this. Normally that is what happens. So if a nuclide X decays by release of a beta particle, the mass number remains the same, but the atomic number increases by 1, and as expressed in this equation. For instance, for example, we can say we can have sodium 24, and this is 11, decay to 24, 12, magnesium, now which is a bit stable, 0, -1, helium. So this one is a beta particle, this is the daughter, and this is the parent nuclide. This is the parent nuclide. So basically that is what happens during beta decay. Now gamma decay. If a nuclide decays by releasing gamma, the mass number remains the same. And the atomic number also remains the same. Remember we said that this one, gamma, is simply enormous amount of heat energy. So for instance, if I have 60, 27, this is cobalt, and I'm going decay, you get 60, 27 cobalt plus gamma. This is not Y, it is gamma. We just write it like this. This is gamma. Gamma. Now, we have come to the end of this short session. Briefly, what we have said, you must be able to define different terms. You must be able to define radioactivity as a spontaneous disintegration of an unstable nuclei to form a stable one. You should be able to define radioactivity in different ways. There are different ways, but the keywords must be captured. The types of radiations, you must know them. We shall come to their deep or their detailed properties in the next session, that is in our lesson number 2. You must be able to explain what happens during alpha decay, beta decay, because we are going to have some questions, some numerical questions that we are going to be handling. So with that, I think I wish you all the best. Continue sanitizing, continue quarantining, and I wish you all the best. I will be doing the next lesson immediately, so make sure you read this one several times, you share with your friends, and if you are willing that I do the next class, you can actually write a yes, text a yes. If you are willing for me to do the next class, text a yes to this number. Text yes to this number, and then we shall move on. I will be doing this chapter, the whole chapter. We are going to move on and on and on, and we are going to see as many questions as possible. Make sure you read, you share this one with your friends you like, and I think we are going to make it. I wish you all the best. Thank you.